Hi, welcome back to the probability lectures here on Educator.com. My name is Will Murray. Today we're going to learn about the geometric distribution. It looks a lot like the binomial distribution in the initial setup because it's kind of describing a similar situation. So I'll try to make it clear how the geometric distribution is actually different from the binomial distribution. The idea of the geometric distribution is that you have a sequence of trials. Each one of these trials can have two outcomes. We think of those as being success or failure. Very typically, you think of this as being a sequence of coin flips. So you're flipping a coin, but it can really be anything where there's two possible outcomes. For example, each year you're wondering whether the Yankees are going to win the World Series. And so each year, either they win the World Series or they don't win the World Series. So there's a yes or no outcome every single time you run the trial. The key point about the geometric distribution is that you continue the trials indefinitely until you get the first success. So, for example, if you're flipping a coin, you would keep flipping a coin over and over again until you get the first head, and then you would stop. Or if you're tracking the Yankees winning the World Series, you would wait and wait and wait as many years as it takes until the Yankees win the World Series for the first time, and then you stop. So the difference between that and the binomial distribution is that we don't know the number of trials in advance, and we stop after we get the first success. Remember, in a binomial distribution, we have a fixed number of trials that we decide ahead of time. We say, I'm going to flip this coin 10 times and I'll count the number of heads. That was the binomial distribution. This is the geometric distribution where we say, I'm going to flip this coin as long as it takes until I get the first head. So that's the difference between those two. You want to be really careful when you're studying a new situation. Am I talking about the geometric distribution or the binomial distribution? So I still haven't given you any formulas for the geometric distribution. The way it works is you have a fixed parameter, which is the probability of success on each trial. So if you're flipping a fair coin, then P would just be 1/2. If you're tracking the Yankees winning the World Series and you figure maybe each year they have a 10% chance of winning the World Series, then P would be 1/10. Q is going to be the probability of failure. That's always 1 minus P. So Q is just dependent on P. You don't really need to know Q ahead of time because as long as you know P, you can work out what Q is. The random variable you're keeping track of is the number of trials that you have to take in order to get that first success. So that's another different aspect between the geometric distribution and the binomial distribution. In the binomial distribution, y was the number of successes that you get in total. In the geometric distribution, y is the number of times it takes to get the first success. So now we're ready to actually get the formula for the binomial distribution. The probability of getting exactly y trials is equal to q to the y minus 1 times p. And here y can be any number between 1 or it can be arbitrarily large. So that's why I put y less than infinity there. This should be fairly easy to remember because what this really represents is q to the y minus 1 means you have to fail on the first y minus 1 trials. If you want to get the first head on your 6th coin flip, that means the first 5 coin flips has to come up tails. So what you're really doing here is you're failing on the first y minus 1 trials. So your first 5 coin flips have to be tails. And then this 1 power of p at the end means you succeed on the yth trial. So if you're flipping a coin, that means on the 6th time you flip the coin, boom, you get a head. And there's a p probability of succeeding on the yth trial. Word of warning here, we have the same bad notation here that we've had for a lot of our other distributions and a lot of our other formulas and probability, which is that we're using P to represent two different things here. So this P right here and this P right here are two different P's That P, remember, is the probability of success on one trial. Probability of success on any given trial, on each trial. So if you're flipping a coin and it's a fair coin, that P is 1/2. If you're rolling a die and you're trying to get a 6th, then that P would be 1/6. This P represents the probability of capital Y, your random variable, having the value little y. So the probability of Y trials overall. And that's unfortunate that people use the letter P for so many different things. It's a curse of the word probability starting with the letter P. So when you study probability, people tend to overuse the letter P. Everything's called P. And unfortunately, you have to keep track that these, even though we use lowercase p for both of these are two different uses of the letter P. So just keep track of that. But having kept track of that, it should be pretty easy to remember this formula for the geometric distribution, because you just remember that you keep flipping the coin until you get your first head, which means you have to fail on all the previous tries and then succeed on try number Y. So you fail Y minus 1 times, that's what the q to the Y minus 1 gives you, and you succeed on the very last time. That's why there's 1 power of P to represent that final success there. So let's keep going with this. There's a couple key properties that we need for any distribution, and I've just listed them out here. The mean, remember, that's the same as the expected value. Mean and expected value are the same thing. Expected value. So the mean or the expected value for the geometric distribution is just 1 over P. The variance for the geometric distribution is Q over P squared. Remember that Q is 1 minus P. If you might see that written as 1 minus P over P squared, depending on which book you're looking at, but those mean the same thing. Standard deviation is always the square root of the variance, so it's just the square root of Q over P squared, which simplifies down to the square root of Q over P. You could also write that as the square root of 1 minus P. That would also be legit to say that that is the standard deviation. Now, there's a very useful fact that I want you to remember from calculus because it comes up a lot when you're doing geometric distribution problems. And that fact is the sum of an infinite geometric series. So let me remind you of the formula for the sum of an infinite geometric series. We covered this in calculus too. If you don't remember this, you might want to go back and review this section of calculus 2 because we use it a lot in probability, the sum of a geometric series. So what we learned back in calculus 2 is that if you have a series a plus ar squared, now that's a geometric series because to get from each term to the next, you're multiplying by r. You're multiplying by r each time. And I didn't write this down on the initial slide, but if this only works if the common ratio has absolute value less than 1. In this case, the sum of the geometric series is given by a over 1 minus r. Now, I think that formula is not very useful to remember. I think it's much more useful to remember the sum of a geometric series in words. And the way I remember it is it's the first term divided by 1 minus the common ratio. Here that first term was a, and the common ratio is the amount you're multiplying by to get from each term to the next. The reason I like that formula better is because it avoids a lot of special cases. If you look in your calculus book, you might see different special cases for the sum of ar to the n, where n starts at 0. You might see one formula there. You might see another formula when n starts at 1 of ar to the n, a different formula. And so you end up having to memorize all these different formulas depending on subtle differences in how the sum is presented. The formula in words is always the same no matter how you give the series. So if you remember that one, you'll never go wrong. So I really like this formula the first term over 1 minus the common ratio. That's what I tend to remember. And when I apply that to adding up the sum of a geometric series, it always works. So let me give you an example of how that comes up when we're studying the geometric distribution. A lot of times when you're studying a probability problem, you want to say, what's the probability that it will take at least a certain number of trials to achieve success? If I'm flipping a coin, what's the probability that I will have to flip it at least 3 times before I see my first head? If I'm waiting for the Yankees to win the World Series, what's the probability that it will take at least 10 years for them to win the World Series? Or what's the probability that they will win sometime in the next 10 years? So the way we want to calculate that is we want to add up all the values that are bigger than or equal to y. So we want to add up, if we want to find the probability that it's at least little y, we look at the probability of little y plus the probability of little y plus 1, little y plus 2, and so on. And we add that up. And I'm just going to use my formula for the geometric distribution. P of y is equal to q to the y minus 1 times p. And so I filled that in for p of y. And then for p of y plus 1, I just incremented the exponent by 1. So it's q to the yp, and then q to the y plus 1p, and so on. That's a geometric series. What we're doing each time is we're multiplying each term by q. So we've got a geometric series. I'm going to use my first term over 1 minus common ratio formula. So the first term here is q to the y minus 1p. Plug that in. The common ratio is q. So that's why I get 1 minus q in the denominator. And now 1 minus q is just p. That was because, remember, q itself was 1 minus p. So 1 minus q is p. And then that cancels with the p in the numerator. And we get just q to the y minus 1. So that's our probability that we will go at least y trials until we get our success. Another way to think about that is that in order for the experiment to last for y trials, say 10 trials, it means that you have to fail for the first 9 times that you run the experiment. So if you're going to run an experiment, run for 10 trials or more, that means you have to fail 9 times. And so remember, q was the probability of failure. You have to fail for the first y minus 1 times. That's why you get q to the y minus 1 there. So let's see how this plays out in some examples. In the first example, we're going to draw cards from a deck until we get an ace. So we've got a 52 card deck here. We just start pulling out cards until we get an ace. Now, a key question you should always ask about selection like this is, do we replace the cards back in the deck before we draw the next one? And what I've told you in the problem is that we do replace them. That really changes the answer. So you want to be very sure that you understand in probability questions, are you drawing with replacement or without replacement? So we're going to draw until we get an ace. We're being asked, what is the chance that we will draw exactly 3 times here? So let's think about that. This is the geometric distribution because we're doing a sequence of independent trials. We're drawing a card, putting it back, drawing another card, or possibly the same card, putting it back, drawing again, putting the card back. And we want to keep doing this until we get an ace, and then we stop. So we want to find out how many cards, how many times we're going to draw until we get that first ace. So let's first of all figure out what our parameter is. Our P is our probability of getting an ace when we draw a card from a 52 card deck. Well, there's 4 aces in there, and there's 52 cards total. So that's 1/13. We have a 1/13th chance of success anytime we draw a card. Q is always 1 minus P, so that's 12/13. That's the chance that we'll fail on any particular drawing. So we have a 12/13 chance of getting something other than an ace. And now let me write down the formula for the probability for the geometric distribution. P of y is q to the y minus 1 times p. In this case, our y is equal to 3 because we want to know the chance that we'll get exactly, that we'll have to draw exactly 3 times. So P of 3, in this case, is Q is 12/13. I'll fill that in. 12/13. Y minus 1 is 3 minus 1, so that's 2. P is 1/13. And now we can, I guess I can simplify that a bit. It's 12 squared over 13 cubed. I don't think I'm going to go ahead and multiply those out because I don't think the numbers would get any more illuminating there. So I'll just leave that as my answer. You could multiply that out and get a decimal if you wanted to. Of course, it'll be a number between 0 and 1, a fairly low number. But I don't think it'll be very revealing, the decimal that you'll get. So that's our answer for example 1 here. So just to recap how we did that, we figured out this is a geometric distribution because we're running independent trials until we get a success. The probability of success is, well, there's 4 aces out of 52 cards, so it's 1/13. Q is 1 minus P, so that's 12/13. Then I just drop those into my probability distribution formula. The Y here is 3 because we wanted to draw exactly 3 times until we get an ace. So I filled in Q, I filled in Y, or Y minus 1, and I filled in P, and then I simplified that down to get an answer. In example 2, we have the Akron Aardvarks, and they're competing in the Northwestern Championship of Pin the Tail on the Donkey. And it looks like they have a 10% chance of winning the championship each year. And I want Y to be the number of years until they next win. So we're sitting there in Akron, and we're hoping that the Aardvarks are going to bring home a trophy this year. We want to know how many years we might have to wait until we see that trophy. So we want to find the mean and standard deviation of that. This is a geometric distribution, once again, because we're waiting for the first success. We're waiting for our home team to bring home that first trophy. So our P, that's our probability of them winning in any given year. It's 10%, so I'll write that as 1/10. Our Q, probability of failure, of them not bringing home the trophy, that's 1 minus P. Q is always 1 minus P, so that's 9/10, 1 minus 1/10. And now our mean, so I gave you the expected value formula, which is the same as a mean, on one of the earlier slides of this lecture. It's always 1 over P, so that's 1 over 1/10, and so that's exactly 10. We want to express that in years. That is not at all surprising. That's kind of one of the more intuitive results in probability. The mean of the geometric distribution, if they have a 10% chance of bringing home a trophy in any given year, then on average you expect to wait about 10 years until they're going to bring home a trophy. So that's not surprising. About once every 10 years they'll bring home a trophy, and so if you sit down to wait, on average it'll take you about 10 years. You'll be waiting about 10 years to see them bring home a trophy. The sigma squared is the variance. Sigma squared, so the first thing we figured out there was the mean. Now we're going to figure out the variance, and that's not what the problem is asking. The problem is actually asking for standard deviation, but the standard deviation is the square root of the variance. So once you figure out the variance, it's very easy to find the standard deviation. You just take the square root. So that's why I find the variance first. The variance is, sigma squared is Q over P squared. So that's 9/10 divided by P is 1/10, so P squared is 1 over 100. If I do the flipty-flipty on the fraction, then I get 100 times 9 over 10. 100 over 10 cancels to 10, so I get 10 times 9, which is 90. Now, the standard deviation, once you found the variance, that's very easy. You just take the square root of the variance. So the square root of 90, I can simplify that a little bit. I can pull the 9 out of the square root where it will turn into a 3. So I get 3 square root of 10. And I just threw that into my calculator before I started this. So what I came up with was 3 square roots of 10 is 9.487. And again, our units there are years. So the standard deviation in the waiting time is 9.487 years. I guess that means if you're waiting for Akron to bring home a trophy and pin the tail on the donkey, you expect to wait about 10 years on average, but the deviation, the standard deviation, is almost another 9.5 years on either side. So you could easily be waiting 20 years, for example, before they bring home their first trophy. So let me remind you how we did each step there. First, I identified that this was a geometric distribution because we're waiting for them to bring home their first trophy. So we're waiting for the first success in a sequence of trials. Each year they go out, they play the championships. There's a 10% chance they win everything. So that 10% is actually the probability. So that's where I got the p equals 10, or 1/10. That came from the 10% there. And then the q is always 1 minus p, so I got the 9/10. Now I just read off the mean and variance and standard deviation formulas from one of the earlier slides in this lecture. You can scroll back and you'll see where those formulas come from. So the mean is 1 over p, that's 10 years. So we expect to wait about 10 years for them to bring home a trophy. Very intuitive result, by the way. The variance is q over p squared, so I filled in my q and my p, simplified that down to 90. The units on that would be years squared, which really isn't very meaningful, so I didn't write those in. In fact, what we're looking for is the standard deviation, so that's the square root of the variance. Always standard deviation, you find it by taking the square root of the variance. Well, you always can find it that way. So that simplified down to 3 root 10, and I made a decimal out of that. 9.487 years is the standard deviation there. In example 3 here, we're going to make things a little more complicated. We were setting up a game between you and your friend, and it's a fairly simple game, but it'll give us some interesting probability. You just take turns rolling a die, and you get to roll first, and then your friend rolls, and then you roll, and then your friend rolls. Whoever rolls a 6 wins, and I guess the other person has to pay them some money or something. So you're both trying to roll a 6. If you roll a 6 right away, then you'll win. If you fail to roll a 6 and then your friend rolls a 6, then your friend wins. And then you just keep going back and forth until the first person rolls a 6. And so we want to ask several questions about this. What is the chance that you will win on your third roll? So on exactly your third roll, you win the game. What is the chance that your friend will get to roll 3 times or more? And then what is the chance that you will win overall? And that includes you winning on the first roll, maybe on your second roll, third roll, and so on. So several different questions here. This is a geometric distribution because if you kind of think of you and your friend rolling the die together, you're going to keep rolling the die until the first 6 comes up. Whether it's you or your friend who rolls the 6, you're going to keep rolling the die until the first 6 comes up, and then the game's over. You make the payoff, or somebody has to wash the dishes, and you don't roll it anymore. So that's definitely a geometric distribution because you're waiting for the first success. So this is geometric. Our probability is the chance of getting a 6 on any given roll, so that's 1/6. And then our q is 1 minus p, so that's 5/6. Whoops, 5 over 6. And now let's go ahead and answer these 3 questions. I didn't really leave myself enough space on this slide, so just hang on to this. I'm going to go to the next slide and we'll answer the questions. So the first question is that you will win on your third roll. So let me remind you that you get to go first. So you roll first, and then your friend goes, and then you roll, and then your friend goes, and then you roll, and so on like that. So if you're going to win on your third roll, that means that we have to get that 6 on the 5th turn of the game. So that's exactly what would happen in order for you to roll, for you to win on your third roll of the game. So what we're really asking here is the probability that y is equal to 5. Let me remind you of the formula for a probability distribution. For a geometric distribution, p of y is q to the y minus 1 times p. And we already said on the previous slide, we already said that our p for this game is 1/6 because that's the probability of getting a 6 on any particular roll. And our q is just 1 minus p, so that's 5/6. So in this case, p of 5 is q to the y minus 1. That's 5 over 6 to the y minus 1. Y is 5 here, so that's to the 4th, times p is 1/6. And I could simplify that down a little bit into 5 to the 4th over 6 to the 4th times 6, 6 to the 5th. So that's the probability that you will win on exactly your third roll of the game. I didn't find a decimal for that. It would be a pretty small number because it's not very likely that you'll win exactly on the third roll of the game. Now, what's the probability that your friend will roll 3 times or more? What that is really asking is, well, your friend rolling 3 times or more, that's the 6th roll of the game, because in order to get to that turn, you have to have 6 rolls or more. So what we're really asking here is the probability that y is greater than or equal to 6. And we worked that out using a geometric series on one of the earlier slides. That's the probability, let me just remind you, the probability that y is greater than or equal to any particular value of little y is q to the y minus 1. We worked that out using a geometric series. You can also think about that as you have to fail y minus 1 times in order to get the success on the y turn or later. So in this case, our q is 5/6. Our y minus 1 is 6 minus 1, so that's 5. So that doesn't really simplify, so I'm just going to leave that in that form. That's our chance that the game will run 6 turns or more in total, which will give your friend a chance to roll 3 times or more. Now, what's the probability that you will win this game? That means you can win on any turn, so this is going to be a little more complicated. The probability that you will win means that the game ends either on the first turn, or that it ends on the 3rd turn, because if it ends on the 3rd turn, that means you rolled last and you win, or that it ends on the 5th turn, and so on. It really means what's the probability that this game is going to go an odd number of turns. So probability of 1 plus the probability of 3, we'll fill in each of these, plus the probability of 5, and so on. That's the probability that you will win this game, that the game will be won on either the 1st turn or the 3rd turn or the 5th turn, or so on. So let me fill that in. The probability of 1, for each one of those, I'm going to use my geometric distribution formula. So q to the y minus 1 times p. And you know what? I'm just going to leave it in terms of p and q for now, and then I'll fill in what p and q are in a moment. So q to the y minus 1p, when y is equal to 1, that's just q to the 0p, so that's p. Plus, now, when y is equal to 3, that's q squared p. Y is equal to 5 will give us q to the 4th p. Y is equal to 7, I'll fill in one more, plus q to the 6th p, and so on. What I see here is a geometric series. This is a geometric series with, now I got to figure out what the common ratio is between each term. I see that to get from the first term to the next one, I'm multiplying by q squared, And to get from that term to the next one, I'm multiplying by q squared, and so on. It's q squared every time. That's why it's a geometric series. So my common ratio is q squared. So I can use my formula for the sum of a geometric series. Remember my formula, the best way to remember it is in words. First term over 1 minus the common ratio. Common ratio. In this case, the first term is p. Common ratio is q squared, 1 minus q squared. And now I think I better fill in what actual numbers for the p and the q squared. So p, where was that? Here it is up here, is 1/6. 1 minus q squared, 1 minus, now q is 5/6, so q squared is 25 over 36. I'd like to simplify that a bit, so let me multiply top and bottom by 36. Let me separate those. Top and bottom by 36 there, so 36 times the top, 36 times the bottom. That'll simplify things on the bottom. So that'll give me a 6 in the top. On the bottom, I'll get 36 minus 25, which simplifies down to 6 over 11. So that's your chance of winning the game. Your chance of winning the game is 6 over 11. Notice, by the way, that's a little bit more than 1/2. 6 over 12 would be 1/2. 6 over 11 is just slightly more than 1/2. That makes complete sense because you have a slight advantage in this game. The advantage is that you got to roll first. So you're a little more likely to get a 6 before your friend is. Now, it's not a big advantage because 6s aren't all that likely when you roll the die. So in the long run, it won't really make a difference who got to roll first. But you do get to pick up a slight advantage by rolling first. And so that's why that 6 over 11 is slightly bigger than 1/2. So let me go over those steps again, make sure that everybody was able to follow them. The key thing here is we're playing this game where you roll and then your friend rolls, and then you roll and then your friend rolls. So you want to keep track of the turns of the game. It's sort of odd, even between you and your friend. Now, if you're going to win on your third roll is the 5th roll of the game. So that's why I put P of 5 here. And then I use my formula for the geometric distribution to get Q to the y minus 1. The y was 5 and times P. And then I just simplified that down to 5 to the 4th over 6 to the 5th. If your friend is going to roll 3 times or more, that means your friend has to get to his third roll. Now, his third roll is the 6th roll of the game. That's why we're looking at the probability that y is greater than or equal to 6. And we worked out that probability generically for the geometric distribution on one of the earlier slides. You can go back and check it out if you haven't watched it recently. But that probability is q to the y minus 1. Another way to think about that, we worked it out using a geometric series before, but you could also think about that as in order for the game to last 6 or more turns, it means we have to fail on the first 5 turns. Fail means we have to not roll a 6 on the first 5 turns. So the chance of not rolling a 6 is 5/6, and so to last 6 turns, we've got to roll something else 5 times in a row. So that's where that answer comes from. Finally, we're asking, what's the probability that you will win? So you get to roll on all the odd turns, the 1st, the 3rd, the 5th, and so on. So we're asking, what's the probability that the game is won on the 1st turn, or on the 3rd turn, or on the 5th turn? So we're adding up those probabilities, and each one of those I used my geometric distribution formula. And the cool thing is that when I wrote all those out, I noticed that I had a geometric series. And I had a common ratio of q squared. So that lets me use my geometric series formula. By the way, I reminded you of that, the geometric series formula, earlier on in this lecture. So you scroll back a couple slides, you'll see that. First term over 1 minus common ratio. First term was p, common ratio was q squared. And then I filled in the numbers for p and q. That came from up here. filled in the numbers for P and Q down here, did a little bit of simplifying with the fractions, and it came down to 6/11. Now, I didn't convert that into a decimal, but one thing I know for sure is that that's a little bit bigger than 50%, which makes sense because you get to roll first, so you're a little bit more likely than your friend to win this game. So it's a very plausible answer that it would come out to be a little bit over 50%. Okay. Let's move on to example 4. Here we have a company that is interviewing applicants for a job. So they have a job opening and they're interviewing their applicants. And in the general population, 10% of the applicants actually possess the right skills. Maybe they have to have knowledge of certain computer applications, for example, or they have to have studied probability. Anyway, 10% of applicants for this job actually are qualified for the job. So the company is just going to interview people over and over again until they find one person who's qualified for the job, and then they're going to hire that person. So we're asking here the probability that they will interview exactly 10 applicants, which essentially means that the first 9 people will be bums, and the 10th person is that qualified person, and they're going to hire the 10th person. Then part B here, we're going to calculate the probability that they will interview at least 10 applicants. So maybe they'll have to interview 50 people before they find the perfect person for that job, but it's at least 10. So this is a geometric distribution because, again, we have a sequence of trials ultimately ending in one success. And as soon as we get one success, as soon as we find one person who's qualified, we hire that person and then we send everybody else away. We stop the interview process right there. So this is a geometric distribution. Let me fill in my parameters here. The probability of any given person being a worthy applicant for the job is 10%, so that's 1/10. The Q is always 1 minus P, so in this case, that's 9/10. And let me write down the some of the formulas that we had earlier on in the lecture because those will be useful for this. P of y is Q to the y minus 1 times P. And the probability that y is greater than or equal to any particular value is just Q to the y minus 1. So let's go ahead and work that out. In this case, for part A, we want to know what's the probability that we will interview exactly 10 applicants. So we'll have 9 failures, and then the 10th person is the perfect person for the job. So that's the probability of getting exactly 10. And from my formula, my Q to the y minus 1 P formula, that's Q to the 9th times P, which our Q is 9/10. So we raise that to the 9th power, multiply it by a single power of P, 1/10. And that's 9 to the 9 over 10 to the 9th times another 10, so 10 to the 10th. I didn't try to find a decimal for that. It would, again, be quite small. If you plug that into your calculator, it should be a very small decimal because it's quite unlikely that we will have to interview exactly 10 applicants. Most likely we'll find somebody earlier than that or probably later than that. Now, let's find the probability that they will interview at least 10 applicants. So that's the probability that y is greater than or equal to 10. Y is the number of people that we interview. And so using our formula up here, the Q to the y minus 1, so that's Q to the 9th, which is 9/10 to the 9th power. And again, I did not simplify that, but that'll be a bit bigger. Well, 10 times bigger than our previous answer. So that's our probability that we will interview at least 10 applicants. So that's our answer for both of these. By the way, we're going to hang on to this example for the next problem, so don't let these numbers and the whole situation completely slip your mind. In the meantime, let me quickly remind you where everything came from here. So In part A, we want to find the probability that they will interview exactly 10 applicants. Now, it's a geometric distribution, so I'm using my geometric distribution formula right here, q to the y minus 1p. So our y here is 10, and so we have q to the 9th times p, and the values of p and q, well, I got the p from this 10% right here. That's the probability that any given applicant will be a success, and the q is just 1 minus that, so that's 9/10. Drop those numbers in and simplify it down. In part B, we want the probability of interviewing at least 10 applicants. At least 10 means the probability that it will be greater than or equal to 10. So using the formula we derived back in one of the earlier slides, several slides ago at the beginning of this video, it's q to the y minus 1, so that's q to the 9th. Another way to think about that is in order to interview 10 applicants, at least 10 applicants, that means the first 9 applicants are failures. So each one of those 9 people has a 9/10 chance of being a failure. That means we have to see 9 failures in a row in order to ensure that we end up talking to at least 10 people. So like I said, hang on to this, to these numbers for the next example, because we're going to use the same scenario for the next example, for example 5. In example 5, we're going to look back at the company from example 4. So if you haven't just watched example 4, you really need to go back and read that one before example 5 will make sense. So check out example 4. There was a company interviewing applicants for a job opening, and each applicant has a 10% chance of being selected. And so we interview and interview and interview until we find a good one, and then we keep that person, and then we stop interviewing. So what we're doing in example 5 is we're keeping track of how long this procedure will take. Apparently it takes 3 hours to interview an unqualified applicant. So 3 hours to interview an unqualified applicant, and 5 hours to interview a qualified applicant. So all of these people that don't meet the qualifications, it's going to take 3 hours each for us to figure out that these people are actually bums and don't deserve to be here. And then when we finally get somebody that we think is qualified, we're going to interview them for an extra 2 hours just to make sure that they really are the right person for this job. And we want to calculate the mean and the standard deviation of the time to conduct all the interviews. How long do we expect this interview process to take at this company? So let me show you how to set that up. We haven't really seen a problem like this before, so this is our first one. So let me set up a variable that represents time here. T is going to be the time. And remember, y is the number of applicants that we speak to. So number of applicants that we speak to. And remember, the deal here is we're going to keep interviewing until we find somebody good. So that means if we find somebody good on the 16th try, that means we interviewed 15 people who didn't measure up, and then number 16 was the good one. So in general, T is, well, we have all the people who don't measure up. There's y minus 1 of them, and each one of those people cost us 3 hours each. It cost us 3 hours to find out that those people didn't actually deserve the job. And then the last person, the person who was good and we actually want to give the job to, we had to do some extra scrutiny on that person. So it took us 5 hours to interview her because we wanted to make extra sure that she was really qualified for the job. So the total time is 3 times y minus 1 plus 5. We can simplify that a bit. That's 3y minus 3 plus 5, which is 3y plus 2. So that's the total time that it takes. And we want to find the expected value, the mean of that, and the standard deviation. Let me calculate first the expected value and the variance of y, because those are going to be useful intermediate steps. So let me remind you here what our P was. Our P was 1/10 for this problem. That's because 10% of the applicants have the right qualifications, and our Q it's always 1 minus P, so it's 9/10 here. And now our expected value of Y, what we learned at the beginning of this lecture is that it's always 1 over P. So in this case, it's always 1 over P. So 1 over 1/10 is just 10. And let me go ahead and find the variance of Y, because that's going to be useful as a stepping stone to finding the standard deviation. So the variance of Y is always Q over P squared. Again, that's coming from one of the first slides in this lecture. You can scroll back and you can find that. So in this case, the Q is 9/10. P squared is 1 over 100. So if we do the flippity-flippity on the denominator, flip that up, we get 900 over 10. So that's 90. So that's the variance of Y. Now, what we really want is the mean and standard deviation of T. So let me go ahead and figure those out for T. We want the expected value of T, but that's the expected value. T was 3y plus 2. And it's time to remember some properties of expectation. In particular, expectation is linear. So we can write this as 3 times e of y plus 2. I can pull the 2 out because expectation is linear. So this is 3 times, now e of y was 10. 3 times 10 plus 2 is 32. So that's the expected amount of time to conduct all these interviews. Our unit here is hours, so let me go ahead and fill that in. 32 hours is the expected amount of time to conduct all these interviews. The variance is more complicated, and I want to remind you of an old rule of probability. The variance of, have I used A and B? No, I haven't used A and B. AY plus B is equal to a squared times the variance of y. There's no b in the answer. So that's an old rule of probability that's very, very useful, and we're going to invoke it right here. Variance of ay plus b. The b doesn't affect it because that's just sort of shifting all the data over. It doesn't affect how much they vary. You get a squared times v of y. So the variance of t here is the variance of 3y plus 2, which is, now if I use my a is equal to 3 and my b is equal to 2, then I get a squared times v of y, but 3 squared is 9, so 9 times the variance of y. And I figured out the variance of y up here was 90, so that's 9 times 90, which is 810. That's the variance. It's not the standard deviation. We're trying to find the standard deviation. So this was variance. This was the mean that we found up above here. And now what I really want is the standard deviation. The standard deviation is the square root of the variance of t, which is the square root of 810. I can factor 81 out of that, which is a perfect square, so I'll get 9 times the square root of 10. And I did calculate that decimal for that. I calculated 9 square roots of 10 is about 28.46. And again, since this is standard deviation, my units there would be hours. So if you're a company and you're planning this interview process, you know that on average about 1 in 10 applicants is going to have the right skills. You want to budget, on average, it'll take about 32 hours to find the right employee for the job, but the standard deviation on that figure is 28.46 hours. I guess that was an approximation. I should be clear that that was a calculator approximation right there. So let me show you how I did that. This is probably one of the trickier problems here. What we wanted to do was write a formula for the amount of time it takes to conduct all the interviews. So think of Y as being the number of applicants and T is the time we spend on them. And what we're doing is all the unqualified people that we speak to, we spend 3 hours each on them. And you think about it, if we're going to speak to, remember the last person we talk to is the person we hire. As soon as we find a good person, we hire her. So that means all the previous people were unqualified. So that's Y minus 1 people. We spend 3 hours on each. That's why we have the Y minus 1 there. And then the last person costs us 5 hours because we want to give that last candidate extra scrutiny and make sure that that person really is qualified for the job. And so we get 3 times Y minus 1 plus 5. That simplifies down to 3Y plus 2. And we want to find the mean and the variance and standard deviation of T, of 3Y plus 2. Well, to find that, we need the mean and the variance of Y itself. And so using those formulas that I gave you on one of the first slides in this lecture, the mean and the variance are 1 over P and Q over P squared. The P was 1/10. That's coming from example 4, the previous slide, because 10% of the applicants are qualified. So your chance of getting a qualified applicant is 1 over 10. The Q is just 1 minus P, 9/10. So you drop those numbers in here, and you get the mean and the variance of Y as being 10 and 90. Now, to find the mean and the variance of T, to find the mean, we're going to use linearity. The mean is linear, so it's 3 times the mean of Y plus 2. So 3 times 10 plus 2 is 32 hours. The variance is not linear. We have this rule right here, which tells us what to do with linear expressions in the variance. So the variance of 3Y plus 2, whoops, I wrote that 2 was really the B, but it turns out that had no effect on the answer because there's no B up here. It's just A squared Y, so 9 times the variance of Y. 9 times, that's our 90 right here, is coming in here. So we get 810. And then the standard deviation is always the square root of the variance. So we take the square root of 810, and I simplified that down and found a decimal down to 28.46 hours. So that's our mean and our standard deviation in the time to conduct all these interviews if you're this company planning for how long it might take to fill your next job opening. So that's our last example. So that wraps up the geometric distribution. You are watching the probability lectures here on Educator.com, and my name is Will Murray. So thanks very much for watching. Bye-bye.